Imagine peering into the very heart of matter, watching atoms dance and molecules transform in real time. This isn't science fiction. It's the reality unfolding at the SLAC National Accelerator Laboratory, where a revolutionary upgrade to the LINAC Coherent Light Source, LCLS, is rewriting the rules of scientific exploration. But here's where it gets mind-blowing. This new X-ray laser toolkit, dubbed LCLS-II, isn't just an upgrade. It's a quantum leap, propelling researchers into uncharted territories of discovery. The LCLS, often likened to a colossal microscope, has long been a beacon for scientists probing the smallest scales of nature. From unraveling the quantum mysteries of superconductivity to deciphering the intricate mechanics of photosynthesis, this facility has been at the forefront of groundbreaking research. But with LCLS-II, the game has changed. The upgrade boosts the X-ray pulse rate from a mere 120 pulses per second to a staggering 1 million. A 10,000-fold increase that has scientists buzzing with excitement. This exponential leap in capability has empowered researchers to reimagine their toolkit, crafting new instruments and refining old ones to tackle questions once deemed impossible. Take, for instance, the qRIXS and chemRIXS instruments, which employ resonant inelastic X-ray scattering, RIXS, to probe the deepest secrets of materials. qRIXS is a photon-hungry technique, with only one photon reaching the detector for every billion that hit the sample. And this is the part most people miss. With the original LCLS, capturing even a handful of photons was an arduous task, requiring days of data collection. Now, with LCLS-II, those same measurements yield results in minutes or seconds, offering clarity and speed previously unimaginable. Georgi Dukovsky, SLAC lead scientist and qRIXS instrument lead, marvels at the transformation. The data is coming in faster and with unprecedented clarity. We can now watch materials transform over time, track energy flow, and even create frame-by-frame movies of dynamic processes. This was simply unattainable before. The qRIXS instrument, unveiled this spring, is a behemoth, featuring a 12-foot spectrometer that swivels 110 degrees, allowing scientists to examine materials from multiple angles with exceptional resolution. Its debut marks the fulfillment of a long-held wish within the LCLS community, though its high photon demands made it impractical until now. Researchers are already leveraging qRIXS to study high-temperature superconductors, materials that could revolutionize quantum computing, medical imaging, and even power grids by transmitting electricity with zero loss. Meanwhile, Christian Kunis, SLAC staff scientist and chemRIXS lead, highlights its transformative impact. We can now study diluted samples under realistic conditions, yielding high-quality data that was previously out of reach. This opens up entirely new avenues for understanding chemical processes, like the intermediate steps of photosynthesis, which could inspire artificial photosynthetic systems. In the time-resolved atomic, molecular, and optical science (TMO) end station, instruments like the multi-resolution cookie box (MRCO) and the dynamic R-reaction microscope (DREAM) are pushing the boundaries of what's possible. MRCO, with its array of 16 electron detectors, captures the precise moment an electron is ejected from a molecule, offering insights into charge and energy transfer at timescales as fleeting as a millionth of a billionth of a second. DREAM, on the other hand, focuses X-rays on individual molecules, stripping away electrons until the molecule explodes, allowing researchers to reconstruct its structure in exquisite detail. James Cryan, SLAC senior scientist and TMO lead, reflects on DREAM's potential. This tool gives us a fundamental understanding of processes like photosynthesis, solar power, and even how DNA funnels energy. It's a game changer, made possible only by LCLS-II's rapid pulse rate. But here's the controversial part. As LCLS-II generates massive datasets, it's also fueling the rise of AI in scientific research. AI models trained on this data can optimize experiments, predict material properties, and even assist in real-time beamline tuning. While some celebrate this fusion of physics and AI as the future of discovery, others question its implications for human-led research. Is AI a collaborator or a competitor in the quest for knowledge? Matthias Kling, Director of Science and R&D at LCLS, is optimistic. This integration of AI technology is poised to transform the research landscape, accelerating discoveries at an unprecedented pace. As we stand on the brink of this new era, one thing is clear. LCLS-II isn't just a tool, it's a gateway to the unknown. What mysteries will it unveil next? And how will its discoveries reshape our world? The answers await, and they're more within reach than ever before. What do you think? Is the integration of AI in scientific research a step forward, or does it risk overshadowing human ingenuity? Share your thoughts in the comments below.